Okay, so what does it mean? So let's remind me of a couple things. How do we reckon positive area?
Reckon
Mhm.
positive area?
Mm-hmm. That's how we describe it in calculus. How do we reckon positive area? Like, for example, let's just, like if we wanted to, what if we want to find, you don't even need to do any calculus to get that. What's the answer?
Here's a 2.
No.
What?
4x?
Wait, there was a rule about this.
4x.
Did you write about it?
Well, there's no real rule on this, but what is this? This is just the line, this is gonna be a triangle, isn't it? Right? Answer's 8. How come?
Good question.
And either that would be.
Was I gone?
I don't know.
That's the area right there, isn't it? That we're looking for. It's just the area under y equals x from 0 to 4. 8. Right?
Yes.
Half base times the height. Okay? No big deal. Okay, but, so that answer's 8. What's this answer gonna be?
What did you?
Negative 8.
Negative 8.
What?
It's negative 8. How come?
Oh.
Because we added up positive area backwards. And you reckon, positive area is reckoned from left to right above the x-axis, right? So when we flip that around, it makes the direction in which I'm adding up the area negative, and so it negates the area, right? So we could say in general that this is true. Here's one thing that's always true then. The integral of f of x dx from a to b is always equal. How is that going to relate to the integral of f of x dx from b to a?
Gonna be negative.
Yeah, they're opposites, right? Okay, make sense? So what if I tweaked it this way? Now what's the answer going to be? That would be the area under that function, right? Negative x is that line, from 0 to 4. So this area down here is negative 8, right? But we're adding it up backwards, so it becomes positive 8. Okay, and we would get, if we just do the calculus, it's not like that's anything that's so profound. That's what we're going to get, right? If I do the antiderivative of this, what's the antiderivative of negative x? Well, just negative x squared over 2, right? So we would end up getting negative 1/2 times x squared evaluated from 4 to 0. So that's negative 1/2 times 0 minus 16, right? Negative 1/2 times negative 16 is positive 8, right? It works out that way. Okay, but it's just something to keep in mind. All right, so here's another one then. Here's another one. And this is probably all I'm going to do today. Maybe do we need to just do like one review problem of how to do it?
I think I understand it now. The first problem, like the wording was weird, wasn't really sure what was going on.
Sure.
I get it.
We are,
I gotta do calculus over break.
Well,
Common good.
common
Sure,
good.
the common's good.
You.
Well,
Did they put the C in the middle in here? I think they must do this in this section.
Yeah, collective.
Yeah.
Which one?
Oh, did you?
I got.
Oh, what the heck did you do that? You ruined the democracy.
Yeah, here we go.
is making sense. Yep.
Wow, that's easy, okay.
Times Fund Thm shell.
Okay,
Okay, so what's the answer to that? Well, what is this saying? Yeah, now I want you guys to be thinking of this in terms of an area, right? That's the area under the function from A to C, plus the area under the function from C to B must just equal what? The area under the function from where to where? From where?
That seems too simple.
It's real simple. What's it?
Really, so it
A
is.
to B, right?
Really?
Everybody see that? Because the areas touch, right? Okay, does C have to be between A and B? No, it doesn't. What if we had something like this? Let's take something simple. Let's take the function f of x equals x, right? And let's go from, let's say that, well, you know what, it doesn't even matter if we take something that simple. We can just do it this way.
Okay, math.
Okay, so now the same thing's gonna work, right? If we take the area from A to C, let's make that the red area. Right? And the area from C to B is the blue area, right? Okay, so then, does it make sense still that that has to be true? So we got the red area plus the blue area. Is that equal to this purple area right here?
Yeah.
It is, how come? Because this isn't really just saying the blue area, is it? It's saying the blue area backwards. Because we're going from C to B, and C in this case is to the right of B, right? So this would be, hypothetically, let's just say that this is equal to 10. And let's say that this blue area down here is equal to 6, right? Well then, if I'm adding it backwards, that's going to be a -6, isn't it? Right, and so we end up with the purple area being 4, right? So it works. It's pretty cool. This works regardless of where C is relative to A and B. As long as the first integral ends where the second one begins, it makes no difference where C is relative to A and B. It's always going to work, right? Because our area conventions are going to take care of that. Because adding it backwards is adding a negative amount, and so we end up with less, right? Make sense? Okay. All right.
Okay,
I think I'm good.
I've got a question.
Yeah.
So, you give us the, things for when it's like I squared, I cubed.
Mhm.
Are those just the same thing for integral?
You don't need those for integrals. That's the whole point. Those are a relic of the method of finite sums,
Right.
right? Which is arduous and not, you know, it's,
Right here, it's saying now in general that for x squared,
Mhm.
which we would apply to that because we can take the 9 out so it's just U squared.
Mhm.
Wouldn't we need that?
No, that's just saying, all that is the first fundamental theorem, right?
So first fundamental theorem is just saying this, right? We know that the area under the curve f of x from A to B is equal to the antiderivative of little f. That's what the capital F stands for, right? The antiderivative evaluated at B minus the antiderivative evaluated at A, which we can write.
Oh, okay.
Remember how we wrote that? We just wrote it as the antiderivative.
Oh, yeah, I have that written down. Okay.
Right.
Yeah,
Make sense?
okay, yeah, that makes sense now.
Okay,
Okey dokey.
all right. So have at it. That ought to get you going.
Well,
Yep.